Hello, and welcome to the lecture for Chapter 25 from Conceptual Physical Science 6th edition. In this chapter, we're going to talk about the weather and the forces that create the weather, the driving forces, right? So where does the weather come from? Now, this chapter, Chapter 25, is our final of 6 chapters covering Earth science or geology. After this, we're going to move past the Earth and talk about the science of astronomy. So we're wrapping up all of our different divisions of physical science. So let's see what there's in store for Chapter 25. Well, we've talked a lot about the atmosphere already, like in the previous chapter. We've talked about the Earth as a whole, ocean currents, how we expect the era of the Earth to make sense relative to the current era when we talked about geological time. So we've definitely had a lot of context to understand weather. So let's get into it. We're going to talk about atmospheric moisture, which is a specific topic that really refers to a interesting phenomenon that leads to dew and moisture and condensation. Okay? Then we'll talk about weather variables in a broad sense. Then we're going to delve into the details about clouds. All right, so you can see some chosen detailed topics: atmospheric pressure, cloud development, really focusing on a few easier to understand topics within meteorology, which is the study of weather. Then we're going to get into air masses, the idea of fronts, which is a term you've probably heard, like there's a front coming in, like a storm, and storms themselves. Then we'll talk about types of violent weather. This will include tornadoes and so on. And then we'll talk about the practice of weather forecasting, which is very much informed by science. Okay, so weather in a broad sense has 4 factors that influence it. Those are atmospheric moisture, so just how much water there is in the atmosphere, how many H2O molecules, the temperature of the air, right, as well as the ground, but just the overall temperature, air pressure, okay, because that does vary. We know there's an average pressure, which is taken to be 101,000 pascals, but that pressure does not hold uniform all the time, even at a given location. Okay, so air pressure can change, and the arrangement of land and water features. So these, certain valleys, certain mountain faces, having water nearby definitely affects weather and the likelihood of certain weather events. Okay, so we got a lot of text here, but this is to help us understand temperature and the idea of water vapor, all to inform our understanding of atmospheric moisture. So moisture in the air. Okay, so temperature is a measure of the average kinetic energy of molecules. This fact has come up quite a bit in this class, right? Quite a bit from this textbook, because every time from the very beginning when we had to define temperature, we had to make it clear that that's what temperature is. It is proportional to the average kinetic energy of individual molecules. So high temperature doesn't always mean high heat, for example, okay? But now we're going to consider temperature in the context of having other molecules in in the air mixture, primarily nitrogen and oxygen. Okay, so at high temperature, water molecules are fast, with enough energy to easily bounce out of the liquid state and into the vapor state. They can easily evaporate. Okay, so water molecules that exist at high temperature can easily change state and become a vapor. Okay, become a free molecule. With increased temperature, there is increased evaporation, and more water vapor will make its way into the air, right? So if you're boiling for something, for example, you're creating a lot of water vapor. Air with a lot of vapor is called humid, a term I'm sure you've heard, okay? So a lot of water vapor in the air means humid air, okay? When temperatures cool, however, what happens? Well, that water vapor, however much is in the air, perhaps a lot, perhaps not that much, but those molecules will slow down, right? Because temperature is proportional to average kinetic energy. That includes the water molecules. And that lack of energy means that they can't easily remain a vapor. They will fall out of the air, they will condense, they will settle, and they'll bounce into each other and stick, which causes them to clump together. This is condensation, because once they clump together enough, then they're heavy enough that they'll drop out of the air, which I'm getting ahead of ourselves a bit talking about rain, but it's the same idea. We even suspended water droplets building up in the air. Depending on the temperature, water vapor may condense to form dew, clouds, or fog, or if cloud droplets get big enough, even rain. And if cold enough, frost, snow, or freezing rain, because then that liquid will change into a solid. Okay, the gas is not going to change directly into a solid. We need that clumping together to begin with, and then we're going to have freezing if the temperature is low enough. So, no matter how dry the air may feel, there's always some amount of water vapor. We actually saw this when we talked about the composition of the atmosphere, and it was small in terms of an overall percentage because obviously nitrogen and oxygen make up 99% of the air. But it's still there, it's always there, and there's always some H2O molecules. Humidity is the mass of water vapor in a given mass of air. So it's a ratio of masses. So mass of H2O over the mass of air. Dimensionless, there's no units of humidity because it is just ratio of masses, which is to say kilograms over kilograms. So obviously those cancel out. So that's why this ratio doesn't have any units, okay? In other words, humidity is the air's water vapor content, right? Helpful way of thinking about it. When air is saturated with water vapor, it is at its maximum humidity. Any additional water vapor, what do you think it will do? It will condense, right? It's maximally saturated. What happens with saturation in a fluid, right? Like water, really, a liquid. It drops out, settles to the bottom. Well, same idea here, but it drops more dramatically, faster because of the low density of air, so it really falls, and we get water droplets, okay? But those, of course, those water droplets do have a terminal velocity. They don't fall at some unreasonably high speed, but they certainly fall faster than salt settling out of fully saturated water. But same principle, saturation and the material, in this case, dropping out of the medium, dropping out of the air. So saturation occurs when the air's temperature drops, because if it drops, then the air can no longer support as much saturation. Saturation is always proportional to temperature, whether it's air or water that's being saturated. And when something drops or cools in temperature, well, then the saturation amount decreases. The temperature at which saturation occurs is called the dew point, okay? So the dew point is actually the value for a temperature, okay? So it's a value for a particular temperature that matches saturation, okay? But it matches that saturation depending on what is the humidity, okay? We're going to bring those back together because it's important to see that connection between temperature, dew point, and humidity, okay? So when the air is saturated at maximum humidity, that's 100% humidity, it has reached its water vapor capacity. Saturation and water vapor capacity are both temperature dependent. They're not fixed values. It's not like air just has one particular maximum amount. It can hold more when it's hot. It can hold less when it's cold. Okay? So the air's capacity for water vapor varies with temperature. Okay, got that? Warm air can accommodate more water vapor than cold air. Higher temperature means more energetic water vapor molecules, more evaporation. Okay, that's why it can hold more. Increased temperature and increased water vapor capacity are tied together. As air cools, it accommodates less and less water vapor. Cooler temperature means slower moving water vapor molecules. Condensation is more easily occurring, thus saturation is more easily achieved. That means the saturation point is lower. Okay, the water vapor capacity is less. Decreased temperature, decreased water vapor capacity. One leads to the other. Okay, so relative humidity is the ratio of an air's water vapor content to its capacity. All right, so its capacity is temperature dependent, but whatever is its current capacity based on its current temperature, well, then you can consider, well, how much water vapor is there based on that current capacity. The capacity varies over a given day as temperature varies over a given day, right? Warmer, you have higher capacity in the heat of the day, lower capacity at night, for example, in a typical day. So is the relative humidity is the most common way to describe atmospheric moisture because it's so useful because it applies to that current value of capacity that is always changing as temperature changes. Relative humidity is water vapor content, which is absolute humidity, divided by water vapor capacity, multiplied by 100 to make it a percentage, okay? Relative humidity depends on the actual water vapor content and air temperature. It's this active value. It's an instantaneous value. It applies to the current conditions. And by the way, a moment ago when I said 100% for maximum humidity, that would actually be only for maximum relative humidity. Because recall, humidity was actually volume per volume, right? It's not related to the current capacity. So it's actually not measured in a percent. It's a ratio. Okay, so maximum humidity would just be however many kilograms of water can be held to however many kilograms of air there is. So it would be some ratio, some fraction. Okay, but the percentage would apply perfectly to relative humidity. I was just getting ahead of myself. I wanted to clarify that. Okay, so this graph that we see down here is a very helpful graph to hopefully visually show what we're talking about in terms of this relationship between absolute humidity, relative humidity, and temperature. Okay, so in saturated air, and of course dew point. Okay, so in saturated air, condensation and evaporation are in equilibrium. All right, so if it's perfectly at saturation, there is just as much condensation happening as evaporation. That means that there's no rain, for example, there's no fog. The air would still be clear air, but it's fully saturated. It's just about to either dry out a bit and have more room for air molecules, or start to actually have condensing water in the form of rain or fog, or even snow if it's cold enough. Okay, so that's perfectly at saturation, a state of equilibrium. Okay, but any change from it is no longer going to be equilibrium. The evaporation rate depends on temperature. I'm highlighting this a lot, okay? The condensation rate depends on humidity and temperature, right? Okay, so when the evaporation rate equals the condensation rate, the relative humidity is exactly at 100% equilibrium. When the evaporation exceeds condensation, the air is no longer saturated, and relative humidity is less than 100%. As I said, more room for air molecules, more room for water molecules in the air. If condensation exceeds evaporation, the air is supersaturated and water droplets form, okay? And get fog, rain, whatever happens to them, okay? So let's take a look at this, because here we have maximum specific humidity, okay? This is the ratio of mass over mass, okay? So this is what I called absolute humidity. This is not relative humidity, okay? And we can see that it varies in this case, not as a decimal, but as just arbitrary values based on the units, because here we're measuring grams per kilogram. So grams of water per kilogram of air. And in that case, there's a lot more grams per kilogram, which is why our values are in this range of 0 to 50, okay? A dimensionless ratio. If we look on the horizontal axis, we have temperature measured in Celsius, degrees Celsius, and we got 0 down to colder temperatures, quite cold temperatures, up to very warm temperatures, okay? And we can see that we have this curve. This curve represents that equilibrium point, that value of perfect saturation, where the evaporation rate exactly equals the condensation rate. So we can see that for those two values to be exactly balanced out on a rather cold day at 0 degrees Celsius, we can't really hold that many grams of water per kilogram of air, somewhere in the range of 5. All right? But as a day warms up to a quite warm day, a very, nice and hot day at 30 degrees Celsius, well, then we look over on the horizontal value and find that that gets us just below 30, maybe somewhere in the range of 28. This one was 5. 28 grams per kilogram. So 28 grams of water per 1 kilogram of air. So quite a bit more water can be held. Now, at any of these balance points, if the amount of water exceeds, then we get droplets. If the amount of water in the air drops, then there's just more room here for humidity, right? So we can have variations in the amount of water just from some cause, right? So maybe a geyser goes off, or maybe there's an external source of water coming in the form of clouds getting pushed by a prevailing wind. Whatever is the source of the water, right? That these things can happen, all right? And also just the evaporation rate can increase, right? Independent of the temperature. Okay, but often the evaporation rate will be tied to the temperature, and so perhaps we'll follow along this curve, throughout a given day. Okay, but hopefully this idea of the regions where the condensation rate exceeds the evaporation rate and where the evaporation rate exceeds the condensation rate, all relative to that curved equilibrium, makes a little bit of sense, because a graph can tell a very clear story if we spend some time with it. So, as we said many times, warm air has a higher capacity for water vapor than cool air. When the air is completely saturated, it is at its maximum specific humidity. Water vapor capacity. At saturation, relative humidity is 100%, and the air temperature is the same as the dew point. Okay? So remember, a dew point is a temperature. All right, you might not know from the term. It's not terribly clear. It's not called the dew temp or something, dew temperature. It's a confusing term in that respect. I would, remember, take note of that because it's easy to forget that a dew point is actually measured in values of temperature, usually Celsius. Okay, but the dew point is that temperature at exactly 100% humidity, and if we are at saturation and the relative humidity is 100%, then the air temperature is the dew point. Okay, so let's look at some examples of temperatures that then and how they relate to maximum specific humidities. Okay, so we see that at 32 degrees Fahrenheit, which I was talking about as a cold day because that's 0 degrees Celsius, we see that the maximum specific humidity is 3.8. Based on the graph, I rounded that to 5, but you can see that this table matches the values that we were talking about in the graph. All right, and same idea here. We could also look at the other one we looked at, 30, and see that that applies to 86 in Fahrenheit, a temperature we're used to, and just under 30 grams per kilogram for how much water can be held in the air. Okay, so to reiterate and clarify the dew point, the temperature at which saturation occurs. Okay, that's what the dew point is. It's temperature. Condensation occurs when the dew point is reached. Okay, so based on the current conditions, the dew point will be known, right? It's often measured, or these days it's reported on some online database. You look at the dew point, and you know then if the temperature drops to the dew point and nothing else changes, then condensation will occur. Fog will roll in, or fog will start to appear in the air, or rain will start. Okay? Water vapor condenses high in the atmosphere to form clouds. Okay? Water vapor condenses close to the ground to form dew, if it's right on the ground, frost, or fog, if it's near the ground. The dew point can be used to indicate water vapor content. High dew point means high water vapor content, because again, that means a high temperature, right? So high dew point must mean a lot of capacity because we know capacity goes up with temperature. A low dew point means low water vapor content. Again, that makes sense because colder air can hold less water. So therefore it has a lower dew point, it has a lower threshold of saturation. Okay, so you can see how these terms are related, okay? And by the way, this whole comment about water condensing high in the atmosphere and forming clouds, often that's the case because the dew point at ground level isn't the same as the dew point hundreds of meters up into the air because of course it cools as you go up in the troposphere. Okay, so the dew point is always less than or equal to air temperature. Okay, it's never greater than the air temperature. The difference between the air temperature and the dew point can be used to indicate whether relative humidity is low or high. So if you see the temperature throughout the day, all right, so let's say, this is, if we have throughout the day and we've got noon over here and we've got midnight over here, okay? So this is measured in time. If this axis here is temperature, so this is the temperature throughout the day, hot at noon and colder at night. And the dew point is going to vary. The dew point is going to be a lower temperature when it's hot and the air can hold more. So it's going to look like this, be very low, but it's going to go up as the air cools. And it might not get there. They might never reach the dew point, okay? May approach the current midnight temperature, but not quite get there. That means 100% humidity was never reached, and we wouldn't expect to find any dew on the grass in the morning. But sometimes the dew point will, based on the particular conditions, get up over the current temperature, and that would be in the winter when frost forms, or in other times of the year when dew is found, on surfaces outdoors. Okay, this would be another example of a dew point. So, as air temperature increases, what happens to relative humidity? Does relative humidity increase? Does it decrease? Or is relative humidity unaffected by temperature? Which is it? It decreases. As air temperature increases, relative humidity will always decrease. Okay? Because the air can hold more. If the air can hold more, then the amount of water vapor that's currently there will not be as close to the total amount or the max amount that can be held. Okay? So as temperature increases, the air is able to accommodate more water vapor. Water vapor capacity increases and relative humidity decreases. But you might say to yourself, well, but what if you just add more water, right? Couldn't you then catch up with the extra space that's being created? Yes, but that's not what we're asking. We're asking for air temperature. The only variable that's changing is air temperature. So if everything else is held constant and you just increase air temperature, relative humidity will always decrease. What about the dew point? When the dew point is high, what happens to relative humidity? Does it increase, decrease, or is it unaffected by the dew point? Remember my little sketch here about a graph and the dew point and the current temperature at different times of the day coming closer together sometimes? If they come closer together, what do you think that means for relative humidity? When the dew point approaches or meets the current temperature, what does that mean for relative humidity? It increases, okay? Because the closer you get to the dew point, the closer the relative humidity is to 100%. If these two graphs are very close together, right? If we have a very close together, zoom in on this a bit, well, maybe they got close enough together that the relative humidity got the 90%, okay? It got really close to having condensation, having dew, right? So the closer they are, whereas they're far apart here, well, here the relative humidity might only be 10% because they're so far apart, okay? So relative humidity decreases as the dew point goes up, okay? So let's think about weather variables now. We've talked a lot about moisture in the air. Let's broaden our discussion. We want to consider temperature and pressure. Now, air pressure is the force exerted by the movement of air molecules into one another. The faster the air molecules move, the greater their kinetic energy and the greater the air pressure. Okay, so heating things up increases pressure. All right, happens in closed containers, also happens in closed atmospheres around planets like Earth. Warm air exerts more air pressure on its surrounding than cool air. Now we got to understand here that that pressure can be actually pushing on other air. So you can almost visualize air as being in large pockets depending on local weather conditions. Now, of course, they're actually, continuous and you have gradients of changing pressure, but air pushes on other air. It doesn't just push off the ground or the edge of space or something. Air pushes on other air. The denser the air, the more molecule collisions and the higher the air pressure. That's the zoomed in individual particle explanation for why higher temperature, and denser, more compact molecules mean greater pressure, right? Just more chances for collisions, therefore greater pressure. Air pressure, density, and temperature are interrelated. Absolutely. That relates to something called the ideal gas law. We mentioned this briefly back in our chapters on thermodynamics. Ideal gas law. There's that relationship. Now, there's something called an adiabatic process. This is a key term here. And it occurs when air is expanded or compressed without heat exchange. So it's usually when air is expanded or compressed very quickly. There's no chance for heat to flow via conduction or radiation from that quickly expanding pocket of air or parcel of air. And so that's considered an adiabatic process. Okay? Okay. So what does that mean? Well, when adiabatic expansion occurs, which relates to some cases of quickly rising hot air, then the temperature of a dry, unsaturated air parcel, decreases by about 10 degrees for each kilometer rise. So in the case where you have a big parcel, shown here, something looks like a lot like a cloud, that is rising up, okay? As that hot air is rising up, it's going to decrease in temperature 10 degrees for every 1 kilometer it rises. This rate of cooling for dry air is called the dry adiabatic lapse rate, which is quite a name for it, right? Pretty long name. But it means that there's this very predictable amount of temperature drop for hot air that's created near the surface and is quickly rising up into the atmosphere, okay, into the troposphere. So this relates to particular weather events, one which is called a Chinook. Now, Chinooks are warm, dry winds, so they're a type of wind that occur when cold air moving down a mountain slope is compressed as it moves, because it's the opposite of this dry adiabatic lapse rate during rising. This is air that's going down, that's sinking, all right? So it's compressing rather than expanding. And as it moves to lower elevations, it becomes warmer. The compressed air warms up. Of course it does. If you decrease the volume and it's more or less an adiabatic process with no heat exchange, then that decreased volume means the temperature must go up. Okay? So adiabatic processes like the lapse rate in rising air or that cool air in the Chinook also occur in moist air. As rising air cools to its dew point, because again, right, dew point's a temperature, the current temperature of the air then can reach that dew point. When the two of them reach each other, you've got 100% humidity and you've got condensation. Water vapor condenses when that dew point is reached, okay? And it's going to be reached at higher altitudes easier than at lower altitudes. Because the process of condensation releases heat, the surrounding moist air clouds or air cools at a lesser rate of only 6 degrees per Celsius for each kilometer rise. Okay, so the idea then is if this is dry air, then we're going to have a 10-degree temperature drop per kilometer that rises up. But if it's moist air, then the process of basically there's an extra way for energy to be dissipated, and so we only get about 6 degrees drop per kilometer of rise. This rate of cooling for moist air is called the moist adiabatic lapse rate, as compared to the dry adiabatic lapse rate. Okay? So, in normal conditions, air temperature decreases with altitude. This rate of cooling varies from place to place and can vary over the course of a day. This rate of cooling with altitude is called the environmental lapse rate. Okay? This idea is you just go up mountains, the air gets colder. The average environmental lapse rate decreases at about 6.5 degrees Celsius for each kilometer rise in elevation. That's because it's not as affected as just pure moist air, because this could be dry air, but just the fact that this is overall environmental effects, and we have to think about radiated energy off the ground, especially if we're near some mass of ground, then we have this average of 6.5 as we go up, okay? And this definitely applies to hiking up mountains. So, if rising air stays warmer than the surrounding air, it will continue to rise instead of returning to its starting position. That's called unstable air, because it's not in a force equilibrium. The buoyant force is greater than the gravitational force. That air will get buoyed upwards. Okay, the buoyant force will draw it up. Eventually, however, that air parcel will expand so much and cool sufficiently to match the surrounding air. Then it will be in equilibrium. When the temperature mass matches, the air parcel stops rising. But it does not sink back to its starting position. Instead, unstable rising air tends to form clouds with vertical development, cumulus-type clouds, okay? So that process led to whatever moisture was in the air condensing, and so now that air is in a new equilibrium with condensed water in it. The stable air resists upward vertical motion and tends to form clouds that spread horizontally. Cirrus and stratus type clouds fall into stable air, okay? So you have this relationship between unstable rising air and stable air that's reached an equal temperature. When upper regions of the atmosphere are warmer than lower regions, which is opposite of what normally occurs, we have a temperature inversion. And you might be thinking, wait, does that ever happen? Well, certainly. Okay, now sure, most of the time you go up the higher elevation, the air cools. But sometimes there's warmer air above. For example, what if there's a high elevation desert with some winds towards the coast? Well, then there could be hot air coming off, all right, creating a region of hot air up above. Okay, and where does this actually happen? The mountains around Los Angeles. Okay, hot air blowing in through mountain passes, leaving hot air above and cooler air down below, because that cool air is being refreshed by air coming off the ocean being cooler, say in the middle of the day, because it has a higher heat capacity and it didn't heat up as much as the ground. And the ground heats up a lot in the case of a city because it's so dark and reflective, as opposed to, say, forest coloration. Okay? So that creates trapped air, okay? Because the air can't continue to rise. If the air is trapped and it can't continue to rise, it can't really get refreshed, can it? That leads to smog. Because otherwise, the polluted air of a city often can just get blown away or just rise up and go away. This happens for a city like San Francisco, for example. But Los Angeles, the air is more likely to get trapped. Okay? So it's a city that's known for its smog issues. So what does the image below demonstrate? Speaking of San Francisco, condensation, air pressure, temperature inversion, or all of the choices being correct? Actually, just condensation. Cool air, cold enough near the surface for fog to form. So let's then review cloud development. We've mentioned some different types of clouds created by stable or unstable air. So we see we can have high clouds, okay? Because what's nice about this is we're just associating them with elevation here, or altitude, I should say. So we have very high clouds above 6,000 meters. Those are our cirrus, our cirrostratus and our cirrocumulus. Then we have middle elevation clouds between 2,000 and 6,000 meters, the altostratus, the altocumulus. Then we have low clouds. These are the ones below 2,000 meters. Stratus, type of cloud, stratocumulus, and nimbostratus. Then there are those clouds created by unstable air that have vertical development, because all these others would have horizontal development because they're in an equilibrium. These include the cumulus and the cumulonimbus. So, clouds develop when the condensation rate exceeds the evaporation rate above the lifting condensation level. A rising air parcel will always cool at that dry adiabatic lapse rate until it reaches saturation. After that point, it will then continue to cool at the moist adiabatic lapse rate as if it continues to rise unless it's reached equilibrium. All right, and that controls how thick the cloud will become. The height of the cloud base and how thick the cloud becomes depends on the environmental lapse rate. So that's just how high we are up, basically relative to sea level, the dry adiabatic lapse rate, and the moist adiabatic lapse rate. Which of the following clouds appears at the highest altitude? So this would be from the table we looked at: stratus, nimbostratus, altocumulus, or cirrus. Do you remember? One of the ones that came first. Cirrus. Cirrus, shown here, are very high altitude clouds, right? Up to 6,000 meters, 6 kilometers above the surface. What happens to the relative humidity of a rising air parcel at the lifting condensation level? Right, so this is tying ideas about cloud formation and these lapse rates or these cooling rates with changes in altitude back to what we were talking about before, relative humidity. So what's the best answer? Relative humidity decreases, marking the upper limit of cloud formation. Relative humidity increases and the air parcel stops rising. Relative humidity increases 100% and the air parcel is saturated. Or relative humidity decreases and cloud formation begins. The best answer is C. Relative humidity increases to 100% at the lifting condensation level, and the air parcel becomes saturated. The lifting condensation level is the mark of the base of the cloud. It tells you at that altitude, clouds can form based on the particular conditions of that day. So each step towards precipitation is part of collision coalescence. That's like those H2O molecules we saw smashing together and either bouncing off or sticking together, right? If they stick together and coalesce, okay, or if they collide and stick together, they coalesce, because coalesce, shown here, means stick together, okay? So this happens due to or affected by the formation of dust, updrafts, growth of stationary drops of water. So it's, there's a chain effect. Bigger drops lead to more bigger drops, and the falling of raindrops. So incoming raindrops from above can also lead to increased condensation and coalescing. Vertical development in the cloud is necessary so that enough droplet collisions occur. You have to have that chain reaction. You have to have drops coming from above that lead to more drops below. Raindrops shrink as they fall because the evaporation rate exceeds the condensation rate once they leave the cloud. So sometimes they never hit the ground. They can actually evaporate midair. If enough evaporation occurs, raindrops may disappear before they reach the ground. This actually has a name. It's called virga. It's like this illusionary rain. You see it, but it never actually hits the ground. So air masses fall into 6 categories, okay? Now what we're doing here is we're not talking about the process of rain anymore, but we're talking about the broader scale, the larger scale idea of air masses, fronts, and storms. The idea, if we zoom out away from the few meter or 100-meter process of clouds forming to an overall landscape or a section of a continent, then that's what we're talking about here. Okay, so air masses on a large scale fall into the categories of Arctic, Greenland, North Atlantic and Pacific, Canadian and Siberian, Caribbean Sea or Gulf of Mexico, and Mexico southwestern United States. Okay, so the Arctic is an example, a classification of a maritime Arctic. Greenland is an example of a continental Arctic. The North Atlantic and Pacific sources or air masses, excuse me, are an example of a maritime polar classification. The Canadian or Siberian are continental polar. Then we have the Caribbean, that's maritime tropical, makes sense because sea and tropical. And then the Mexico or Southwestern is continental tropical, right? So these are all different types of air, and they all have their own symbol, right, as you can see. So the 6 that are general classifications are these ones here. Their application to ones that are near a viewer that's watching this or a student that's in North America are going to be these ones here, right? These are local regions that have this type of air mass, okay? And as far as the characteristics, they're what you would expect. Arctic air masses are cool, moist, and unstable. Unstable part is maybe not so clear, but they are. Greenland air masses are cool, dry, and stable, all right, or continental Arctic. Maritime polar are cool, moist, and unstable, okay? So a lot of the same characteristics between maritime polar and maritime Arctic. Continental polar are cold, dry, and stable. Maritime tropical are warm, moist, usually unstable. And continental tropical are hot, dry, stable aloft, so stable up high, and unstable below. So they actually have a splitting of stability. All right, and here are some examples of air parcels all around the United States. So, what about another broad scale phenomenon? Well, that's atmospheric lifting. Well, we've talked about the idea that warm air rises and we can consider the rate at which it cools based on those adiabatic lapse rates. So it's a general theme. Air rises, okay, the lifting of air. Now there's 3 types of phenomenon that lead to the lifting of air. Convection lifting, which involves cumulus clouds, orographic lifting, which is a rain shadow. So that's the air getting pushed up over a mountain range. Orographic is referring to the land being in the way and pushing the air up. And frontal lifting, which forms cirrus clouds changing to cumulonimbus clouds. Okay, so here's an example of convectional lifting. Here's an example of orographic lifting, that air getting pushed up and over a mountain range, right, with a rain shadow. Okay, so very little rain on that side of the mountain. And here's an example of frontal lifting, where there's no actual physical mountain made out of soil and rock and minerals, but instead there is a mountain made out of air. There's a big cold air mass with higher density, and so the warmer air gets pushed over it, just like air gets pushed over a mountain, okay? Right? And here is a warm front getting pushed over a mountain of cold air, okay? So frontal lifting has more dynamics to it, which would make sense because it's not fixed on the shape of the mountain, but it can change depending on what, the actual cool air mass and what it's doing. So we have an occluded front, right, which is shown here, right, in terms of that lifting up over a front of air. I think this shows it very well. We have the warm air, right, going in 2 directions over 2 pockets of cold air. One pocket is probably colder and kind of has a rounded look to it. The other one is less cold and is very gradual, linear. This creates very different clouds in the 2 directions. So we call it occluded because it's got that split as the warm air rises in 2 directions. Okay. Then we have the next kind, all right, which is showed here, all right, where or next step, excuse me, where the 2 different cold air fronts come together, right, can still continue to create different clouds in different directions. And then eventually the larger, colder pocket of air starts pushing the less cold pocket of air out of the way. And we have the clouds forming together, right, and the front continuing to change. Sort of those 2 fronts forming as one. Okay, so the occluded front starts with a V shape and ends with more or less a straight line. So a cyclone is an area of low pressure around which wind flows. Okay, so continuing on with these large-scale air phenomena. Due to the Coriolis effect, and again, just to reiterate the Coriolis effect, this is the idea that because the planet is spinning as a whole, but the circumference of the equator is much greater than, say, the circumference near one of the poles, the land is not moving at the same rate. In other words, the land is moving faster along the equator. That means the air is getting carried along relative to the land faster at the equator as well. That means you have faster moving air at the equator, slower moving air closer to the poles. That creates friction between all that air, which creates these large circular structures on a global scale. the Coriolis effect or Coriolis force. Okay? So winds in a cyclone move counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Air converges in the center of those large structures, the region of lowest pressure, all right? And it is forced to rise upward. What is the name for a front that occurs when a cold front and a warm front merge? Occluded. That was the only one we really focused on. So, continuing on the broad scale, storms, an example of violent weather. They're defined as violent and rapid changes in the weather, right? If you need a formal definition of a storm, that's what it is. There are three major types of severe storms: thunderstorms, tornadoes, and hurricanes. Thunderstorms begin with humid air rising, cooling, and condensing into a single cumulus cloud. When fed by unstable moist air, a cumulus cloud grows into a thundercloud. The thunderstorm contains immense amounts of energy. All thunderstorms include thunder and lightning, otherwise they're not a thunderstorm. The electric energy flowing from the cloud to the ground is lightning. So that energy will find a path to the ground. Those electrons will find a path where they don't have to be so closely packed together. That path is into the ground where they can be evenly distributed in essentially infinite mass of the Earth relative to the tightly packed electrons in the cloud. As lightning heats up in the air expands, and that's the thunder, right? That's the sound of the expansion. Okay, tornadoes, on the other hand, are funnel-shaped columns of air that rotate around a low-pressure core that reaches from a cumulonimbus cloud to the ground. A funnel cloud is similar to a tornado, but it does not touch the ground. Okay, so funnel clouds can become tornadoes. Okay, not all funnel clouds do. Tornadoes are dangerous because of their suction, because they will suck things up, and they have an upward force, and also the battering from their high winds. Hurricanes are the greatest storms on Earth, right? In sheer size and energy, by far. The energy comes from latent heat released from condensing water vapor. Okay, so that process of condensation releases energy. That energy builds up in these large cloud structures. The rising warm air creates low pressure near the surface, drawing in more moist air. The wind rotates around a central low pressure area, the eye of the storm. There's a continuous supply of energy from tropical waters. You can't get hurricanes without warm waters. A hurricane weakens as the fuel is cut off. Once it starts going over land, for example, they always weaken over land, right? So as they make landfall, as we call it, and enter areas of cooler water. So strong vertical wind shear in hurricanes or violent weather in general can cause warm air to tilt inward and spiral. It can develop into a tropical depression. Okay, tropical depressions are like pre-hurricanes. In the same way that a funnel cloud can become a tornado, tropical depressions can become hurricanes. If the storm intensifies, it progresses into a tropical storm, okay, with increased wind speed. Then there's a cutoff point where we define it as a hurricane, and that's once there's any winds in that storm that exceed 300 kilometers per hour, which is an exceedingly fast wind. So what is the eye of a hurricane? Is it an area of high pressure? Is the area of highest precipitation, low pressure, or is it where the upper level air descends? Okay, it's low pressure. The eye of the storm is a region of very low pressure. So weather forecasting is the predicting of weather, right? It's what news stations do, but they use information to be able to predict the likelihoods of, say, fronts moving in a certain direction, storms rotating at a certain rate, okay? So weather forecasting involves collecting data from all over the world. Like incredible amounts of data go into these forecasting algorithms, go into these computer simulations. Computers can plot and analyze data and predict weather. And the models just get better and better by machine learning processes, so computers learning themselves, and through direct human intervention, humans increasing the quality of the program by including new variables, for example. All right, although the many variables make accuracy difficult, indeed, because we're talking exceedingly complex interactions. Weather symbols are used to represent data for various locations: sky cover, wind direction, speed, dew point, temperature, and pressure. All the things we talked about are regularly reported by weather reports. On a weather map, these station models are used to draw lines of equal pressure, which are called isobars, iso meaning the same, bar referring to pressure, which are used to represent frontal systems. So we can clearly show these big fronts by those big lines of isobar, equal pressure. And that brings this lecture to a close and brings our unit on geology and earth science to a close. I hope this lecture has been interesting and informative, and you're looking forward to talking about astronomy in the very next chapter.